Okay, hello everyone. Today we will learn about the sampling distributions and the central limit theorem part 2. And so we will cover the central limit theorem and then the proof of this. And I think the central limit theorem is probably uh, one of the important theorems in statistics. So let's learn about it. Suppose y1 to yn is a random sample from a normal distribution with mean mu and variance sigma square. And to do the inference about mu, we usually use y bar, and especially we use this formula, y bar minus mu divided by the standard deviation of y bar that follows normalized distribution with mean 0 and variance of 1. But however, in most of times, we don't know sigma square. So we usually uh, we we put estimate for sigma square, which is s square, and so we put s instead of sigma, and then the next question arise is that what would be the distribution of this thing? That's the question, and actually the theorem in the last later slide talk about this. Okay. Here comes the definition 7.2. Let Z be a standard normal random variable and let W be a chi-square distribution with V degrees of freedom. Then if Z and W are independent, then if we define T is Z divided by square root of W divided by V, this one follows T distribution with V degrees of freedom. So this is the definition for the T distribution, and let's define our Z as this quantity, which follows standard normal distribution, and let's define our W as this thing. And in the previous lecture, in the lecture last week, we learned that this one follows chi-square distribution with n-1 degrees of freedom, and we also proved that y bar and s square are independent. So we can define our t this way. We can define our t as z divided by square root of w divided by v, and then that's this one, and this can be simplified as this one, and so this follows t distribution with n-1 degrees of freedom. So this is what we usually use when we are doing the inference, and if we don't know the uh, sigma square estimate. Okay, and here is figure 7.3, and it's describing about the comparison between standardized normal and t distribution. And what we know is t distribution have heavier tail than standard normal distribution. And also as n goes to infinity, as n goes large, t distribution is getting closer to standard normal distribution. So if it usually when n is large, then we can approximate our t distribution with standardized normal. Okay, let's move on to example 7.6. The tensile strength for a type of wire is normally distributed with a known mean mu and a known variance sigma square. Uh, 6 pieces of wire were randomly selected from a large roll, and yi, the tensile strength for portion I is measured for I equals 1 to 6. Okay, and the population mean mu and variance sigma square can be estimated by y bar and s square respectively. And because sigma square of y bar is sigma square divided by n, and so this quantity can be estimated as square divided by n, and find the approximate probability that y bar will be within this range of the true population mean mu. And before we, so what we want to calculate is we want to approximate probability of y bar within this range, y bar minus mu within minus 2s square root of n and 2s divided by square root of n. So we want to estimate this probability, and before we do that, what we know is yi follows normal distribution with mean mu and variance sigma square, and both of parameters are unknown. And what we also know is that y bar follows normal distribution with, again, mean mu and n over sigma square. That's what we know. And since we don't know the exact sigma square, probably we will use so y bar minus mu divide by s square s over square root of n. This follows t distribution with with n minus 1 degrees of freedom. So what we will use is this one, since we don't know the sigma square. So to calculate this probability, this is actually probability of y bar minus mu divided by s over square root of n. And this is between minus 2 to 2. And so we know that this follows t distribution with n minus 1, which is 5. And so we can calculate the probability using the t distribution. And so that's what we want to calculate. And so so if you calculate this quantity by using t distribution, then this would be end of the proof. Okay, suppose that we want to compare the variances of two normal populations based on information contained in independent random samples from the two populations. So in both, so we have two populations, and a sample size of n1 and n2 are taken from the two populations with variances sigma 1 square and sigma 2 square. And intuitively, to compare the variances, S1 square, so estimate for sigma 1 square would be S1 square, and estimate for sigma 2 square would be S2 square. And so to compare the two variances, one of the measure would be this one. S1 square divided by S2 square could be used for the inference to compare about the two variance components. And the next question would be, what would be the distribution that this thing follow? And let's learn about it. Okay, let's move on to definition 7.3. Let W1 and W2 be independent chi-square distributed random variables with nu1 and nu2 degrees of freedom. Then F for this quantity, which is chi-square divided by chi-square, is set to chi-square, actually chi-square divided by its degrees of freedom divided by chi-square divided by its degrees of freedom. Then it's said to have an F distribution with nu1 and nu2. nu1 for denominator degrees of freedom, and nu2 be denominator degrees of freedom. And we can use this F distribution for the inference of um, our comparison in the variances. So let's define our W1 this way and W2 this way. And we know that W1 follows chi-square distribution with N1 minus 1 degrees of freedom, and W2 follows chi-square with N2 minus 1 degrees of freedom. And since all the samples are independently sampled, so uh, the this S1 square and S2 squares are independent. And so let our F as this. Let our F as W1 divided by nu1 divided by W2 divided by nu2. Then this one should follow F distribution with N1 minus 1 degrees of freedom and N2 minus 1 degrees of freedom. Okay, and so, how can we do the inference about sigma 1 square and sigma 2 square? So, um, let's assume that sigma 1 square and sigma 2 square are equal. If we assume that sigma 1 square and sigma 2 squares are equivalent, then S1 square divided by S2 square would follow F distribution with N1 minus 1 and 2 minus 1 degrees of freedom. And so if we can look for the probability of this, and if the probability of this event is very rare, then we may conclude that sigma 1 square and sigma 2 squares are not equivalent. So this is the definition for F distribution. And if what we observed, um, so our F distribution is like this, and if we observe that our observation is very rare, I mean the calculating the area here, if it is very rare, then it would be a kind of evidence that sigma 1 square and sigma 2 square may not be equivalent. That's how we do the inference about the variance using F distribution. And we will probably learn this later in next semester. Okay, let's move on to example 7.7. If we take independent samples of size n1 equals 6 and n2 equals 10 from two normal populations with equal population variances, find the number b such that this. And actually we assume that equal population variances. So and also we know that S1 square divided by uh, sigma 1 square and S2 square divided by sigma 2 square. This follows F distribution with 6, 10. And since we assume equal population variance, these two canceled. So what we know that this one follows F distribution. So we can calculate this quantity B by using F distribution table. And in the textbook, in appendix table, we have table for F distribution, and you can look for the quantity B. And actually, you should find that P, this S1 square, S2 square is greater than or equal to B, and this is 0.05. You should look for table for this, and you can find B by yourself and try this. Homework for chapter 7.2 are these. Okay, now let's move on to chapter 7.3, the central limit theorem. And I think this would be one of the most important theorems in statistics. And let's learn what this means. the central limit theorem. Suppose y1 to yn is a random sample from any distribution with mean mu and variance sigma square. Then we know that the expected value of y bar is mu and variance of y bar is sigma square divided by n. We can still do the inference about the population with y bar, even if we don't know the distribution of yi. Yeah. Mm, but if we know that all the yi's are independently sampled from the same distribution, and if we know that mean is mu and variance is sigma square, then we can do the inference about y bar. Uh, Actually, y bar follows normal distribution as sample size goes large, and this result is called the central limit theorem. Okay. Let's take an example to understand about the central limit theorem. Suppose that y1 to yn is a random sample from exponential distribution. So your sample yi is sampled from this distribution, exponential distribution, and if you take 5 samples from exponential distribution and calculate y bar from those 5 samples and look at the distribution of y bar 1000 times. So what you do is you randomly sample 5 from exponential distribution and measure y bar for those 5 samples, and you do it 1000 times. So you will have y bar 1 and y bar 2 dot 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 y bar 1000, and after you getting y bar 1 to y bar 1000, take a look its distribution. That would be the result of figure 7.6, and this is how it looks for sample mean of when n equals 5. It's a bit skewed, but uh, it's much more. So this is exponential distribution, and the distribution of y bar with 5 samples, it's more like uh, bell-shaped than the original distribution. And if we increase the sample size, if we look at when n equals 25, and it looks more normal, it looks more normally distributed. And this is what the central limit theorem implies. As n goes to large, we can approximate the sample mean with standard normal distribution. That's what the central limit theorem implies. I found an interesting online simulator. This is a simulation of randomly selecting thousands of samples from a chosen distribution, uh, and the purpose of this simulation is to explore the central limit theorem. You will learn how to population mean and standard deviation are related to the mean and standard deviation of the sampling distribution. So if the original distribution is uniform distribution, it's like this. And if we have 2 samples, then mean of these two, the distribution would look like this. And however, if we make our population size large, like when n equals 9, and then the distribution for its mean of 9 uniform 9 samples from uniform distribution looks like this. When n is 25, it looks more normal, and when n is like 100, it's more like normal distribution. And let's try to new distribution, like skewed left. Um, so the distribution here skewed to right. Uh, I don't know. Yeah, this side. And when n equals 2, the distribution is still skewed. However, as we increase the number of samples, and we can check that the distribution becomes more like normal. Let's try to uh, the skewed right, and then actually this is similar. When n equals 2, it's a bit skewed, but if we make our sample size larger and larger, this the distribution of the mean follows can be estimated with normal distribution. Okay. Okay, finally we have the central limit theorem, which is theorem 7.4. Let y1, y2, and yn be independent and identically distributed random variables with mean mu and variance sigma square. And if we define un as this one, then and where y bar is sample mean, then the distribution function of un converges to standardized normal distribution as n goes large. Okay, and you can find the CRT simulator that I explained in later slide from here. And and To use this central limit theorem, I usually write this way: y bar follows normal distribution with mean mu and variance sigma square divided by n. And if we write this way, then you can you know that y bar minus mu divided by sigma divided by square root of n follows normal mean 0 and variance of 1. And so I usually write this way or this way, and um, and then solve the problem with CRT. Okay. Okay, let's move on to example 7.9. The service times for customers coming through a checkout counter in a retail store are independent random variables with mean 1.5 minutes and variance 1.0. And we may not know the distribution. And the problem is to approximate the probability that 100 customers can be served in less than 2 hours of total service time. Okay, so we should match the time unit. So 2 hours, which is 1 hour is 60 minutes. So 2 times 60 is 120 minutes. Uh, and also we have 100 customers. So what we want to know is yi. Sum of I equals 1 to 100, and sum of yi's. And let's say yi follows some distribution that we don't know, but this is the service time for one customer, and the expected value of yi would be 1.5 minutes, and variance of yi is 1. And we know we want to find the probability that sum of all these service time is less than 2 hours, which is 120 minutes. And so we want to know the probability of this thing. Okay, and from CRT, when the customer n, the number of customer is 100, by CRT, we may approximate the sample mean with this. Y bar follows a normal distribution with mean 1.5 minutes and variance 1/10, square root of 100. And so, um, so we can convert this probability as y bar. So divide by 100 and times 100. Oh, divide by 100. Okay. And so y bar. So this is now y bar, and y bar minus 1.5. 1.2 minus 1.5, and divide by 1 over actually this is 100. This is variance. So here this is the square root of n. So this part is actually sigma square divided by n. So it's 1 over 1 over 100. And here this is 1 over 10. Okay. Sorry for the confusion here, and so this one, and we know that this probability can be approximated as the standard normal, and we can calculate this is 3 maybe. uh, let's see, -3 actually, 0.3. Minus 0.3 times 10. Okay, so you can approximate the probability using normal distribution. Okay. Let's try to solve one more exercise problem. The downtime per day for a computing facility has mean 4 hours and standard deviation 0.8 hour. Suppose that we want to compute probabilities about the average daily downtime. For a period of 30 days. And the number one, what assumptions must be true to use the result of Theorem 7.4, which is the theorem for CLT, central limit theorem, to obtain a valid approximation for probabilities about the average daily downtime? So we want to do inference about their population mean, y bar, follows normal distribution with mean mu and mm, sigma square divided by n. And to use that, what the assumption that we need is our samples y1 to y30. Since we have 30 days, um, we need the IID assumption, independent identically distributed. So y1 to y30 follow from the same distribution that we don't know, follow from same distribution, and also they are independent samples. So we need this assumption. Y1 to y30 is IID from an arbitrary distribution, and then we can use the central limit theorem to approximate the distribution for y bar, uh, the average daily downtime. And under the assumption, second problem, under the assumption described in part 1, what is the approximate probability that the average daily downtime for a period of 30 days is between 1 and 5 hours? 1 and 5 hours. This is what we want to calculate. And in here, actually, by CLT, y bar follows normal distribution by CLT. Y bar follows normal distribution with mean 4 hours and the variance 0.8 squared divided by 30, n is 30. Okay, this is what we know, and so y bar minus 4 divided by 0.8 divided by square root of 30 follows normal 0, 1. Okay, so to calculate this probability, we should normalize it. 1 minus 4 divided by 0.8 divided by square root of 30. And also square root of y bar minus 4 divided by 0.8 divided by square root of 30, and this is 5 minus 4 divided by 0.8 divided by square root of 30. And from the normal distribution, you can calculate this quantity, and you can answer the question A. Okay. Okay, let's move on to number B. Under the assumptions described in part A, what is the approximate probability that the total downtime for a period of 30 days is less than 115 hours? Okay, so probability of total downtime, which is y bar times 30. That would be the total downtime for 30 days is less than or equal to 150 hours. Okay, and previously we calculated the distribution for y bar that follows normal distribution with mean 4 and the variance 0.8 squared divided by 30. This would be the by using CLT, y bar follows this thing. And what about 30 times y bar? This follows normal 4 times 30 and 30 times 0.8 squared. So 30 times y follows the normal of this. So you can approximate it using this. So 30 times y bar minus 120 divided by square root of 30 times 0.8 squared, which is less than or equal to 115 minus 120 square root of 30 times 0.8 squared. Okay, so this one uh, is z standardized normal. So this thing is probability of standardized normal is less than or equal to the quantity here. You can, I think you can calculate it by yourself using your calculator, and then you will get the probability using a normal table or something, or by computer. Okay. And homework problem for chapter 7.3 are these. Okay, so far we have learned about the central limit theorem, and we will prove the central limit theorem in next lecture. And also in next lecture, I will give a example that using central limit theorem, and then I will end the class of this semester in the next lecture. Okay, thank you.